Okay guys, in this video, the second video of a two-part series on IR spectroscopy, I will continue through the handout packet and we will look at a number of different IRs. We will interpret peaks, and along the way we will see just about each and every one of the different types of functional groups and bond types that you will commonly see in IR spectroscopy. We'll begin with this compound here. Pretty darn simple. This is just an alkane, 1, 2, 3, 4, 5, 6. So what we have here, C6, it's all saturated, C6H14. What type of bonds? Since I have compound here, I'm going to start by looking at what types of bonds are present. I have C, single bond C, and then I have CH. But all of the CHs, what's the hybridization of the carbon? They're all sp3. Where do these give absorbances at in the IR? This is a single bond that does not contain a hydrogen, so this is going to be fingerprint. Fingerprint roughly about here, down somewhere. That or that is due to that. C single bond. We don't need to identify it. What is this down here in the non-fingerprint region? We should identify that. Pretty substantial absorbance just below the magical line of 3,000. Well, we know that that is our sp3ch. Okay? There you go. Nothing else there. That's really not an absorbance. Well, we need to learn when is it a peak, when is it not. There's no absorbances here, not much here, and then fingerprint. Okay? One word of caution, there is 14 CH bonds in this molecule. That does not mean we're going to get 14 absorbances. We may have strong, we may have weak. You cannot quantify like that in IR, at least not easily, and not at the introductory level. We know that we have some sp3ch, and indeed we do. Okay? Next compound. The compound below, what's new? Well, what's old? We have lots of sp3ch. All that's just condensed. That's all sp3ch. Here with this alkene, we now have the C double bond C. We also have carbon H. 2, 3 of them, where the carbon is sp2. Magical line here at 3,000. sp3ch, right below 3,000. We now have a peak just above 3,000. What's that for? That's your sp2ch. Looks like it's maybe one peak. Even though we have 3 bonds, it doesn't matter how many peaks. We have absorbance here. We have sp2ch in the compound. What about the CC double bond? Remember from a table, you got to get used to looking at your tables. Okay, we can look back at our table. We got an alkene. Where do we expect a peak? At about 1650. Do we have a peak at about 1650? 15, 16, right there. Nice strong peak. What is that peak? Exact value, 1640 something? Let's see. 1642. Reciprocal centimeters. You could turn that into actual centimeters, and from there you could turn it into microns or something. Okay? This is our C double bond C. From there we have fingerprint, which is where you get absorbances for those bends and wags and all types of things we showed on the wiki. I see this peak here about 18 something. That's like high carbonyl. Obviously there's no carbonyl here. What is that? Well, this is a good chance for us to point out what an overtone is. I'm thinking it's probably an overtone of this strong peak. This peak is about 900. Exactly 910. 910 reciprocal centimeters. What can happen sometimes is this means some type of frequency or vibration absorbed the IR pretty well. Okay, that means it may be a WAG or something. I'll do it as a bond. Okay, it absorbed. It went from here, absorbed and went from to here. Absorbance took place. 910. You can turn that into energy if you like. I reckon that's some of your Gen Chem conversions. What can happen is it can do a double jump. And the bond can be minding its own business. Instead of going here, it can absorb twice the energy and go here and be very high energy. Now to go do a double jump, it takes about twice the energy. This is higher energy. You can actually just double this number and we get about 1820. This peak here is 1821. I think it's an overtone of that there, where some of the bonds, or whatever this is for, absorb twice the amount of energy. Overtones are very common. You've got to learn when to look for them. Very often we'll see overtones with carbonyls that will give a overtone at somewhere maybe here. They tend to be weaker. They don't tend to be that strong. Okay, what's different from this IR? This peak and this peak. A little more activity here because we have a little bit more diversity in functional groups. This next compound, we have an alkyne, carbon-carbon triple bond, and so we have a CH, where the carbon is sp hybridized. Got to know your hybridization. We have sp3ch in this long chain here. Not too long, it's only about 4 carbons. What else do we have? CC single bond, well that's fingerprint. Well, we got the CC triple bond. Remember triple bond region? About 2200. A little bit less for this. Let's see what we have here. I've got a strong peak at about 3300. If you look at your table, it's this guy here. And it's strong, just like that table says. Magic line, if I can draw a straight line, this is your SP. Uh-oh, what need you to tell me? sp3ch. Here. What is this peak at about 2120? Well, there's your absorbance for that. Where the molecule was sitting there minding its own business, this triple bond was stretching. The IR light came in at about 2120 reciprocal centimeters, or you can turn that into wavelength or energy, and we got an absorbance. And the absorbance was plotted. Rest is pretty much fingerprint. A little something there, potentially overtone. Got a huge peak down here in the fingerprint region. Not sure what it is, but it'll be there 5,000 years from now, if you run the IR in 5,000 years. Okay, so there's an alkyne. Now, with the alkyne has an H, which has to occur at the end of a chain. That's called a terminal alkyne. The next alkyne will be an internal alkyne. And what we're going to do is look at the difference in the intensity of this peak for that functional group. I'm going to line this up right on the 3000 so I don't have to erase that. Look what's missing. There's no intense peak for the SPCH because these carbons don't have an H on them. Not there. A little tall, small peak there. I think we're probably just going to ignore that. We do have sp3CH, which I just erased. There you go, just below 3000. Also have sp3CH here. Where's this guy? About 2200. There it is, okay? Not that tall. It's actually 2054. Actually a little bit lower energy, lower wave number. The more important thing here I want to point out is look how less intense it is. Okay? It's less intense. Internal alkynes tend to be, peak tends to be much less intense, pretty weak, sometimes even absent. The reason is because of these carbons on each end, as opposed to a carbon and an H, there's less polarity here. Because there's less polarity, the absorbance is weaker. Stronger, it turns out, with a terminal alkyne rather than an internal. The rest is fingerprint. Note how that fingerprint is clearly different than the fingerprint above. Okay, in this compound we have an aromatic ring, benzene ring, which is sort of the grandfather of all aromatics. We also have lots of sp3CH, very common component of organic molecules. There you go. Huh. There we go. Let's draw a straighter line here. It's a magical line there at 3000. Looks like we have peaks to the left, obviously. What is that to the left? Well, each one of these carbons has an H. Okay? You got to know carbon makes 4 bonds. There's an undrawn H on each of these. So there's 5 sp2CHs. So this would be sp2CH, sort of there, and that seems to be above 3000. But we have activity there because we have that structural component. CC single bond fingerprint. Well, what about these double bonds? This is your aryl double bonds. This is going to be, if you look back at your table, it said probably about 1550, 1600, somewhere in there. Typically, this type of ring peaks kind of here and here. This peak is almost carbonyl. I mean, it's 16 something, 1603. Yeah. Obviously, there's no carbonyl here. But what if you didn't have structure? You may think, well, carbonyl. There's 2 reasons why that is not apparently a carbonyl. First off, 1603 is a bit too low. The lowest you'll see is probably about 1625 to 30 for your amides. It's also too weak. Carbonyls tend to be more intense, like these guys. Okay? That's probably part of the aromatic, which gives sort of like a couple of 2-3 peaks in here for sort of the bending here, maybe the individual carbon-carbon double bonds. The other thing I want to point out is this region right here. blip, 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 about 1600 to 2000. I call this sort of a mountain range. And this is characteristic of an aromatic ring. A lot of this is due to lots of types of vibrations that that ring as a whole can take on. We don't need to get into that. But if you look at previous IRs, they didn't have this sort of mountain range through here. I also call that an aromatic signature. This compound from the IR just looks aromatic, with the benzene again being your most common aromatic ring. We'll see examples of this moving forward. The compound below, what's unique or different compared to the other one? No sp3ch. All H's are on sp2 carbons. So if we come over here, draw our magical line at 3000, we see that everything is to the left, and there's actually no absorbances to the right because there's no sp3ch. Aromatic, we have sort of peaks here, 1500, 1600, and then we've got this mountain range. Pretty pronounced here. In other cases, it won't be as pronounced. CCl, what about that bond? Well, it's a single bond with no H, so that should be fingerprint. So, one of these peaks, you can look in even more precise text, some upper your advanced organic text, and you can find where just about any type of bond will give a peak. Probably one of these here. Next up is an alcohol. This will be a 3-carbon alcohol called 1-propanol. Of course, sp3ch. Look at here. Obviously a very intense absorbance. And what is this here? This is our OH bond from the alcohol. If you remember, OHs do tend to be pretty intense, about 32, 3400 region. Word of caution though, in the modern day instruments that have come out in the past 10 to 15 years, the OH is not quite as intense. It's because of the method that is used. Today the compound just sort of sits up top, and the IR light sort of reflects off the molecule, off the compound, and then it goes and hits the detector. So it's more of a reflectance. In the old days, the light actually had to go through the sample. You had to make a sort of an opaque disc. There was much more prep time. Sometimes your disc would work, sometimes not. But because the light went totally through, you had stronger peaks, particularly down here. And so this is more of a classical, older-looking alcohol absorbance. The rest pretty much fingerprint. This compound here is just an ether with saturated CH on both sides, so we have sp3 CH. Magical line. Notice there's no OH, because obviously there's no OH here. There's a little bit of blip over here. I wouldn't assign that as an OH. If we didn't know structure, that could potentially be an NH. You do have to sort of learn when we want to really consider a peak or when we might disregard it. That takes practice, asking questions. Obviously, if you have structures in front of you, that can't be an NH because it's not in the molecule. For the rest, fingerprint. One time we can look into fingerprint. This comes up. You see this strong peak right here? This is probably the CO single bond. Typically a very strong peak at about 1100 to 1200 reciprocal centimeters. That's one time to look down there because that does usually a strong peak. We see this in ethers, also in functional groups like esters. We can use this sometimes as a last resort if we need additional information to help solve what we're trying to solve. Here we have a primary amine. We have sp3CH. We have two NH bonds. Or we can say two NH peaks in the IR. Note that they're not as intense as OH. We also have this peak here. It's kind of odd looking. It's about 1600. Clearly it's not a carbonyl. Maybe an overtone of a peak that's about an 800. That's pretty intense. Maybe it's an overtone. One thing I can say about these two peaks down here, this here, it's not two individual NH peaks. This is sort of just a minor point. It's actually where you have, one of these absorbances is from the symmetric two-bond stretch, and the other absorbance is from the asymmetric two-bond stretch. And these have different frequencies, leading to two different absorbances. But in the end, two peaks typically means two NH bonds. Next compound is a secondary amine, has two carbon groups on the nitrogen. sp3CH. We just have one NH peak. A little weak, a little some broadness here. This could be due to water. If this is an actual spectrum, there may be a little water contamination which has OHs that can lead to some of that. Almost looks like a little cow udder there coming down to a point. And the rest fingerprint. NH, sp3CH. The rest is all single bonds, either CC single bond or CN single bond, fingerprint. Next compound is a tertiary amine, three carbons attached to the nitrogen. Lots of sp3CH, which we have here. All of that's that. Note that there's no NH. We see no NH peak. So it's not present here. The rest is pretty much fingerprint. The rest is single bonds. You cannot even tell the presence of the nitrogen from the IR. The presence of the nitrogen would have to be told by some other techniques such as mass spec, elemental analysis, or a couple other techniques. Compound below is an aniline, nitrogen bonded to an aromatic ring. It's an N-methyl aniline. We've got the NH, so we should have an NH peak. Indeed we do. at about, I've got it shifted, it's about 3,400. A little more intense than the other amines. One thing we can note here is when the lone pair of the nitrogen is conjugated, that is, it's conjugated with the adjacent p orbital. This p orbital is all the way around here. This conjugation polarizes the NH bond more, and because it's more polar, the peak is more intense when you have conjugation. sp3, well, we need to draw a magical line. We draw a magical line, we have sp3ch, but we also have peaks over here, which is for what? Each hydrogen on this ring contains, or is a sp2ch. Gives peaks over here. Let's get rid of this, all the p orbitals. Aromatic ring, we have peaks in the 1500, 1600 region. We also can look for an aromatic signature. Have a little bit through here. It's not as pronounced as one of the last ones we saw, like with the chlorine. But some activity here, activity here. It looks like an aromatic compound there. Now we'll turn to our functional groups or compounds that contain a carbonyl group. This here is a ketone. Carbonyl bonded to two plain carbons. We can look for the carbonyl. Here we go. A nice carbonyl peak. At about 17, 18. Standard carbonyl range. We have sp3ch. Fingerprint. One thing we can point out here is, what is this little peak here? It's obviously not an NH or OH. This is most likely an overtone of this here. Intense peaks often give overtones. We can confirm that by doubling this. So times 2 is going to be 34, 36. You can look over here. This is 34, 16. Likely an overtone of the carbonyl. Double, and then very often it's minus just a touch. So just a touch less than double. Fingerprint. Here we have a carbonyl with carbon on one side. This is condensed. You need to be able to know the full structure here. Other side H, aldehyde. Aldehyde has carbonyl, standard range. There you go. About 17, 18. I think it's the same as the one before. Also probably an overtone of the carbonyl. sp3ch. But what about this guy? That's sp2ch. There's nothing above 3,000. That's because the sp2ch of an aldehyde actually gives peaks in the 27, 2800 region. You'll notice right here, I have a peak right there, and then there's also one right there at that tip, and those two are your aldehyde sp2ch. that is often forgotten about by students. So don't forget that one. The rest being fingerprint. In this example, we have an ester. Okay? Carbonyl bonded to carbon on one side. Of course, it's bonded to the carbon. A lot of times this will be shown like this. Sometimes it's better to show the H's on the outside, so you can see the carbon-carbon bond. Carbonyl, carbon on one side, O carbon on the other, ester. Carbonyl, there you go. If you remember, esters are a touch higher than standard. Instead of 1720, more like about 1743. We also have our sp3ch. And then what looks like probably an overtone of the carbonyl. The rest is fingerprint. Pretty intense peak at about 1100-1200, if you remember what that might be, and likely is. Your CO single bond. Right here. One time we can look down there. Compound below is another ester. You can take a look at that on your own. It does have an aromatic ring, so you do want to look for sort of the aromatic signature and sort of peaks in this region. Carbonyl, sp3, sp2ch there. Next compound has a carbonyl bonded to a carbon on one side, nitrogen on the other, and so this is an amide. It's actually a primary amide, because with amides, the nitrogen can have substitution and it still remains an amide. Carbonyl. If you'll note, this is fairly low carbonyl at about 1639. Looks like to me. See how that's low? And as we said earlier, amides do have low carbonyls. The reason for that is because of conjugation. Okay? You got your two p orbitals for your carbonyl. One electron, one electron. Well, this lone pair over here, I don't have enough room to show it. That lone pair sits in a p orbital also, and it overlaps with this pi system here. So that's conjugation. You have to understand that. Conjugation typically lowers your carbonyl value. If the carbonyl is conjugated with something, either a lone pair or a ring, it will lower the value. You get the most lowering whenever it's conjugated with a nitrogen lone pair, and thus your amides. Compound below is a secondary amide because the nitrogen is bonded to two carbons. Should have a low carbonyl. Indeed we do. Low carbonyl at about 16, looks like 15, 16, looks like 1650. I don't know why this looks like a 15 there. That's a bit odd. Yeah, it looks like a 15. Obviously it's 15, 16, 16 something there. I'm thinking it should be about 1630 or so. Not quite sure what's going on here. Carbonyl, we have sp3CH, it looks like, and sp2CH. Indeed, we have sp3CH here, and then here around the ring we have sp2CH. We have a very intense NH. If you remember, we said the conjugation also makes the NH more intense. This nitrogen is conjugated with the carbonyl, lowering the carbonyl, making the NH pretty intense. The rest being fingerprint. Next we have a tertiary amine, carbonyl here. Pretty intense peak, carbonyl region, pretty low, 16. Looks like 1626. We're getting quite low there. We have here at 3000. sp3CH, sp2CH, sp3CH, sp2CH. What is this here? There's no NH in the structure, so we don't expect it. This is perhaps a little water. These are actual spectra. If you've got a little water in your sample, you will get some absorbance here for the water. Of course, water does have OH bonds. Excuse me. I'm thinking that's maybe what that is there. The rest fingerprint. We do have an aromatic activity in the 1600 regions. The aromatic signature is not that intense or almost absent. Sometimes that's the case, not sure why. One below is a primary amide with no aromatic ring. You see, there's certainly no aromatic signature, and there's less peaks in the 1600 region because there's no aromatic. Do have a carbonyl. Interesting here, it's kind of split. Sometimes your amide carbonyl is split. That can be very misleading if we don't know structure, because this could make you think you have two carbonyls in your structure. It's a rare example that you will see. It just turns out that this one, it is split. We could talk other places about potentially why. We have all the H's are sp3CH. And so everything's to the right. And then we have two NH peaks. Pretty intense. I think I know why. It may be because this compound may be a liquid. But pretty intense. Actually, after saying that, I see that that's the reason why is because we've already said it. The nitrogen is conjugated. And when the nitrogen is conjugated, it makes the NH bond more polarized, and that's why the NH peaks are pretty intense. Okay, just a couple of more compounds in this segment as we look at different IRs. Here we have what's called an acid chloride. It comes from a carboxylic acid. It's turned into the chloride. Still have a carbonyl. What we see here is the carbonyl and acid chloride tends to be on the high range. This is about 1800. And if you remember from the table, that's indeed where we said for acid chloride. The rest is sp3ch. So we have here, and then we have fingerprint, perhaps an overtone of the carbonyl there at about 34 or 35, 3600. Compound below, similar example, you can look at this. It does have an aromatic ring, and so we've got these peaks at about 1500, 1600. Carbonyl high, and then we should have peaks on both sides of 3000 because we have sp3ch and also sp2ch. Of course, the C single bond chlorine is going to be fingerprint. Carboxylic acids. Carboxylic acid is probably the king of the functional groups. In Organic 2, we'll learn that just about all functional groups can be made starting with a carboxylic acid, either in one step or very often 2 or 3 steps. A key feature of the IR of a carboxylic acid is that the OH peak tends to be quite broad, and it's quite evident here. Broadness. It goes from being just 33, 3400. That broadness spans all the way down to like 2600. It actually tends to obscure the SP, your CH region, sp3ch, which might be here, but it's kind of obscured. This is a bit odd to have these fine details here. Other than that, you do still have the carbonyl. Here, standard carbonyl, this one is a bit wide, or broad, at about 17 to 1720. Got a little ridge on it. Not quite sure why, and I'm not sure that's relevant. The rest, pretty much fingerprint. You can really see it's not aromatic because we don't have these sort of sharp peaks in sort of the 1500, 1600 region. The carboxylic acid below does have an aromatic ring, and so we see these sharper peaks in that region. Some aromatic signature, but it's pretty weak there. The broad OH is still sort of there, but it's less intense. That can vary per sample, depending on if the compound's a liquid or a solid. You do get some differences. Word of caution again, your carboxylic acids in the lab here using modern instruments, going to be more like this here. Previous one where it's very intense, you don't get that intense absorbance using the modern instruments. But you still kind of see that broadness there that you don't see otherwise. The broadness is due to the extensive hydrogen bonding between one molecule and another, the intermolecular hydrogen bonding. This brings us to a nitrile or cyano group. C triple bond N. If you remember your triple bond region at about 2200. We look here, and indeed we have a pretty strong peak for your nitrile here at about 2230. You see it's just above 2200. We do have aromatic. Pretty good aromatic signature. It looks pretty busy all the way across, really. We got sort of your intense peaks at 1500, 1600 for the aromatic. We do have sp2CHs. And so if we draw our line here, this peak is on the high side, and so that's sp2CH there. And there's not really any absorbance on the low side or the sp3CH region. The compound below is really just the miscellaneous one. The main point of it is that you'll notice that the carbonyl is pretty low. It's also not the strongest peak there. That's actually stronger. The carbonyl is more like about 1670, 1680. That's because it's conjugated not only by the aromatic ring over here, because there's a p orbital there, it's also conjugated by the alkene. So it's doubly conjugated, and this lowers the carbonyl below 1700 into about 1680. Otherwise, you should be able to interpret it yourself. There's no sp3CH in this compound, so you can look for that. Aromatic signature here. Okay, this is not showing up entirely well here. The copy was not good for some reason. But I'm going to end this second video by mentioning some IRs, or showing you some IRs from the research lab. It got hole punched there, but this is a compound made by one of my research students. It's a parole aromatic with the nitrogen here. Main thing, let's look at the NH2, the amine. And so over here in the NH region, we have these two NH peaks. We have the CH region here. Your S double bond O, that's actually fingerprint, even though it is double bonds, because the sulfur is heavier than a carbon. But let's focus on this. This compound was made, and in the next step, what we wanted to do is we wanted this nitrogen to bond to this carbon here and to displace the bromine. And so we did the reaction, we isolated a product, and then what we did at that point is we ran the IR of the product. When we did that, let me show you what we got. Again, the copy is not great. This is in the handout near the back of the packet. But what we got is an IR spectrum that showed only one NH peak. Nice sharp peak here. And of course, the fingerprint region is different from the previous IR. Well, what we were trying to make is, as I said, we wanted the nitrogen to bond to that carbon. We end up actually making it on the ring, and the bromine has been lost. But in this product, there's only one NH bond, and so we only expect one NH peak. That right there exhibits how you can simply use IR to tell if you've accomplished the transformation that you want. Now, does this prove that this indeed is that structure? No, not necessarily. You need other evidence, other spectral evidence, physical data. What it does prove is that it's no longer the other compound. Clearly a different fingerprint region. Now we only have one NH. What it does is it supports this structure. Then we can go on and get additional data. and hopefully all data supports this structure, then you have a convincing argument that you've indeed made the compound that you propose that you have. Indeed, we did get additional data on this compound, but the point I'm trying to make is IR can be a very quick look at what you've done to your molecules, what type of functional groups you now have in your molecules, or what maybe has been eliminated from your molecule. There'll certainly be more IR discussion as we go along. I hope these videos have helped. There's a good amount of work for you to do on your own to come up to speed. The ultimate goal is, one of the goals is to be able to do problems such are found in the workbook. So I hope that you will get started on working those types of problems and asking questions along the way.